Okay, acceleration in terms of velocity. Now, if you want to get something with time in it, then you use dv on dt, and that's what you replace the acceleration with. And if you want to get something in terms of x, then you replace acceleration with v dv on dx. So this is when you have your acceleration in terms of velocity. So once again, if you want to get it in terms of time, then you go dv on dt equals fv. And then if you split that, so you get fv dv equals 1 dt, and then you just integrate both sides. But if you want to get acceleration in terms of x, then you go v dv on dx, and you make that equal f of v, and then you bring all the v's together, so it's v on f of v dv equals 1 dx, and then you just go ahead and you integrate both sides with that one. Okay, so they're like your two different options there. Okay, so let's look at the question. So a particle moves such that its acceleration will equal v squared plus 4. So we've got a few things there. We've got initially the particle is at rest, so that's v equals 0 when x is 4 meters to the right of the origin. Okay, which direction will the particle go after its initial position? Now, we don't have, because it's initially at rest, we don't have a velocity to tell its direction. But if the acceleration is positive, see the acceleration equals v squared plus 4, which will always be positive, then this particle is going to initially move to the right. Okay, so part B, because this is like having a force coming in the positive direction, then the particle will go in the positive direction, so it'll move right. Part B, find v in terms of t. Okay, so v equals x squared plus 4. So if we want v in terms of t, acceleration equals x squared plus 4, replace acceleration with dv on dt, and you get x squared plus 4. And then that means that, I have made a mistake there. It's not x squared plus 4. It'd be good if I could just, it is v squared plus 4. Okay, so we just have it in terms of v and t. So you move this one over to that side. So you get 1 over v squared plus 4 dv equals 1 dt. And then you just go ahead and we integrate both sides here. So the first one is a tan the minus 1 of x on 2, 1 on 2. And the right-hand side is just integrate 1 with respect to time. You just get t. And then you get your constant plus c. So let's use the initial conditions. T equals 0. I keep putting x, but it's actually v for velocity. V equals 0. So it's a half tan the minus 1 of 0 on 2 equals 0 plus c. So that means 0 equals c. Okay. So now we have v. If we look at this, we have the a half tan the minus 1 of v on 2 equals t plus 0. So the 0 disappears. So now to put that back into the form so I can make v the subject, tan the minus 1 of v on 2 equals 2t, because you just move the 2 to the other side. And then that just means that v on 2 equals tan of 2t. So v equals 2 tan of 2t. And that's velocity in terms of the time. Okay, so that's part 1, getting the velocity in terms of the time. All right, so part 2. Let's have a look at that. So now we want to get x in, we've got velocity in terms of time, we're going to get x in terms of t. So if we want to get x in terms of t, first of all, let's write the velocity in terms of time. So it was 2 tan 2t. Okay, so I want to get x in terms of t. So I need to replace the velocity with dx on dt, which is 2 tan 2t. And now I'm just going to, we'll put that'll be 1 equals 2 tan 2t dt. I'm just going to split it, integrate both sides. So here we get x, and on this side we get, now that'll be 2. Now it's going to be sine 2t on cos 2t dt. Now the derivative of cos 2t is minus, needs to be a minus there, but we also need that 2 back in because that's part of the derivative. So it's minus 2 sine 2t on cos 2t. So when you integrate that, you get log. You get ln, like a log with a base e of cos 2t. Now, I did put the minus in there because the minus wasn't there. The 2 was already there, but the minus wasn't. So it'd be minus ln cos 2t. And then we go plus c. That's what x equals. So if I put in time equals 0, x equals 0, that will allow me to go and get what my c is. Cos of 0 is 1, and ln of 1 is 0. So 0 equals 0 plus c, so c will equal 0. So that means that x will equal minus ln cos 2t. And that would be your displacement in terms of time. So we've got so far, we have the velocity in terms of time and the displacement in terms of time. Now the next thing is to get velocity in terms of x and then acceleration in terms of x. We now have acceleration in terms of v. So velocity in terms of x. So let's go d. So if we start with acceleration equals v squared plus 4, and I want to get velocity in terms of x, so I replace the acceleration with v dot dv on dx is v squared plus 4. Move the v squared plus 4 to the other side. So I get v squared plus 4 dv equals 1 dx. And then we're just going to integrate both of those. So the first one there, that is a log. So it should be 2.5 because the derivative of v squared is 2v. So it's a half ln v squared plus 4 equals, the integral of 1 is x plus c. Alright, so that means we've got ln v squared plus 4 equals 2, actually I should find the c first. So v is 0, x is 0. So that's a half ln, v is 0, that's going to be 4, plus, equals 0 plus c. So c is a half ln 4. You can actually simplify that a bit because you can go half ln 4 to the power of a half, because you can bring that up as an indice. Power of a half is a square root. Square root 4 is actually 2. So it's just ln 2. And that kind of makes it a little bit nicer because it's just ln 2. So that means that you have a half ln v squared plus 4 equals x. Okay, and then it is plus ln 2. So if I now times everything by 2, because I'm just going to make v the subject, so it's 2x plus 2 ln 2. So it's v squared plus 4 equals e to the 2x plus 2 ln 2. Alright, so v squared equals e to the 2x times e to the, now 2 ln 2 is ln 2 squared, okay, and then we're going to go minus the 4, this 4 here, I'm going to subtract it on the other side, and I'm just splitting this just to make it a little bit nicer. So that's e to the 2x, e to the 2 ln 2 squared would just be 2 squared, because e to the ln a is just a, and then it's minus the 4. So v squared equals 4, e to the 2x minus 4. There's actually a common factor of 4 there, and you got e to the 2x minus 1. So I'm just going to square root the other side, go 4 e to the 2x minus 1. Now you notice I put plus or minus, but we're just going to take the plus because it will actually end up going in the positive direction, 2x minus 1, because the acceleration initially is positive, so that means the force is going to act in the positive direction. Okay, and that's your velocity in terms of x. Now, if we would like to get the acceleration in terms of x, so that's part E, because we have the velocity in terms of x, so we have v equals 2 root e to the 2x minus 1. To get the velocity, the acceleration in terms of x, probably the easiest way is to use d/v dx of a half v squared for your acceleration. You could use v to the v dx, but I often find when you're going down to acceleration, using this one actually does make life a little bit easier. So x double dot equals d/v dx of a half times 2 root e to the 2x minus 1 squared. It does make it easier because when you square it, the square root part will go. So that'll be a half times 4, and you've still got your d/v dx, and that will be e to the 2x minus 1 when you square it. A half of 4 is 2, so it's d/v dx of 2 e to the 2x minus 1. And when you differentiate that, you get 2e, 2 times 2x minus 1, minus 2. Differentiate the 1, you get 0. And then it's times the 2, and 2e to the 2x. So it's going to be 4e to the 2x. That's going to be your acceleration. So I just think it's, to go from velocity to acceleration, very often it is easier just to do d/v dx of a half v squared. But I find going from acceleration back up to velocity, sometimes this formula become a bit easier. And if you're going up to the displacement, then making the velocity dx on dt and then splitting it, then I think that often helps to get x in terms of t. Okay, so just looking at another one. So v equals 8 minus x. Initially it's at the origin, so time equals 0, x equals 0. In which direction is it travelling initially? So you have v equals 8 minus 0. So v equals 8 minus 8 meters per second. So it's travelling initially to the right because it's a positive velocity. Okay, so find a in terms of x. All right, so in order to find a in terms of x, we have v equals 8 minus x. See, this is where I often find it easier just to go x double dot is d/v dx of a half v squared. And then I just sub v in and I halve it and differentiate it. So that's 8 minus x squared. Okay, so if I differentiate that, I get a half times 2. 8 minus x to the 1 times minus 1. So it's minus 8 minus x, which equals x, positive x minus 8. Okay, if you did it the other way, and it will work, very often if you've got a v squared or a v equals the square root of something, that's when this one is particularly useful because the v squared will get rid of the square root. So if I did v dv on dx, and that's what acceleration equals, then the v is 8 minus x, and dv on dx is the derivative of that, which is minus 1. So it's minus 8 plus x, which is x minus 8. So you could use either one. This one comes in very handy though, if instead of just having a nice v, which equals 8 minus x, you might have v equals the square root of 8 minus x. And then it would be easier just to use that formula rather than the other one. So that's what your acceleration equals in terms of x. So find x in terms of t. So x in terms of t, you've got v equals 8 minus x. That means we need to go up, so that means we need to integrate, and we need to replace the velocity with dx on dt. So looking at this here, I'm going to put the 8 minus x on this side, and I'm going to put the 1 dt on the other side, and then I'm just going to integrate both sides. Left-hand side with respect to x, so that's minus ln 8 minus x, should be an absolute value, and 1 just goes to time plus c. So initially it is at the origin, So that means you have minus ln 8 minus 0 equals 0 plus c. So c equals minus ln 8. So that means that minus ln 8 minus x equals t plus ln 8. Ln 8 minus x equals minus t minus ln 8. Now I might just group the lns together. So you get ln 8 minus x plus ln 8. Because equals minus t. I group them together because it just makes it easier to get the e function happening when you've got it in this form. Because then I've got ln a equals like b, so that means a equals e to the b, because ln a is just log base e of a equals b. And if you apply the seventh rule, which is base to the power, e to the b equals a, then you can remove the log part. So looking at this, that becomes 8 times that because that was a plus in the middle. So that's ln 64 minus 8x equals minus t. So if I apply the basic log rule to this, e to the t, so e to the minus t, equals 64 minus 8x. And then make 8x a subject. So move that over first, and that's 64, and move the minus e to the minus t to the other side. And then divide by 8. So 64 divided by 8 is 8, minus 1 on 8 e to the minus t. So x is 8 minus 1 on 8 e to the minus t. And that there gives you displacement in terms of time. Okay, so what have we done so far? We've got acceleration in terms of x, tick. We have display x in terms of time. And then the question is, what happens to the particle as time goes to infinity? So let's look at the displacement time graph, this one. And if we're looking at as time goes to infinity, what actually happens is if you have an e function, e to the minus t is 1 over t. And as time goes to infinity, the bottom gets bigger and bigger, like it's e to the infinity. That will go towards 0, because 1 over a very, very big number, it's big, will equal 0. Like you think it will approach 0. You think about it, 1 over 10 compared to 1 over 100, 1 over a million. 1 over a million is 0.00001. So it's getting quite small. This is 0.01 and this is 0.1. So it's actually getting closer and closer to 0. And that's what we say, it is approaching 0. So overall, if you're looking at that equation which is above, which is this one, you get x equals 8 minus 1 on 8 times 1 on e to the t, which is 8 minus 1 on 8 times 0, which is 8 minus 0. So the x value will actually approach 8 meters, and that's your limiting. We call that the limiting because it's like a limiting value. It's a value it will never actually hit. It gets closer and closer to, and it will never get bigger than it. So it will actually approach 8. So it's called the limiting displacement, because there's a limit on the displacement.